the measurements. I'm sorry, I'm saying the wrong one. I'm saying these opposite here. The ground truth SWE on this axis becomes larger than the one on the y-axis. And if you look over here, this shows all of the SWE, right? And so again, perfectly from the passive microwave satellite, it should follow this black line, but it doesn't. Instead, what it does is it goes out this way. And so if the ground SWE says 400 millimeters, the passive microwave SWE is only saying 150. And that's because there's saturation with the passive microwave. So if we look back at this graph, what happens is that so much of the signal is scattered that this signal going to the satellite is very, very small. And that way we just can't see deep snowpacks. So passive microwave works best in sort of like in the US, in the Midwest area, which you guys might not be familiar with, but sort of in the plains where there's not a lot of snow accumulation and it's flat. And that's really why we use this reconstruction method. The pixel size has something to do with that too. So I think those are probably two good reasons. I didn't go into depth with this. Oh, depth. The equation that's used generally for the passive microwave is this equation here. And there is more sophisticated, work that's done, but there's not a lot you can do to get better results. And again, going back to this graph here, basically, you can see here that at 100, if we look, this is snow water equivalent on the x-axis. At 100 centimeters of snow here, the signal is basically flat, and that's why that saturation occurs. So does that answer most of the question? Feel free to follow up if there's a follow-up question.
Okay, looks like we just got one more question from Tim. Do you want to take this one, Carl?
Yeah, let me just read it actually.
You can read it out loud for everyone if you want.
Oh, right. Okay.
Yeah.
In lecture 2, roughly at minute 25, you display a great graph of net flux segmented by geographies such as distinctive latitudes, Himalaya, Rockies, and Antarctica, displaying dynamics and distribution. As you move away from the equator, how predictable does this net flux follow a steady downward trend? So let me bring that graph up real quick. So forgive me for not putting the reference on this. These are both from colleagues of mine. I don't actually know who did this one, but it's pretty predictable because it all has to do with the sun's angle. So the sun is directly overhead at mid-latitudes often, and that is why the solar radiation is so high. And I didn't go into depth.
Sorry, really quick, do you want to explain what each color is on that graph? Which component of the radiative flux the colors of the bars are? Okay.
So there is no legend on this graph. And, I think probably the blue is long wave. And I can't actually tell you which ones are the sensible and latent heat, but they're probably the two smallest, the purple and the green. Yep. The yellow is the solar and the red is the net. So the question was, how quickly does the net radiation decrease, or does the solar radiation decrease? And so most of the flux, as we talked about in this graph here, looking at the hourly plot, which is the red line here that comes up, is from the sun. And so we know from geometry where the sun is at all times. And as you move further and further away from the equator, the sun gets lower and lower in the sky. And that depends on the season, of course, and the Earth's tilt, but it's very predictable. And I can add, in the next lecture, I can put a graph or two in to show a little bit more about some models that do that. We sort of use sophisticated models that estimate the sun's position relative to the Earth to do that, but there's also some simpler parameterizations that can be used depending on latitude and also depending on cloud cover.
And I'll just add that this graph here on the left, we're going to be making these graphs in today's lab using real data from a field station that we manage. So we'll be going into more detail on all the components of energy balance throughout the lab today. Any other questions from anyone before we move on to the lab exercises?
Are there any questions specifically on the reconstruction or energy balance? I think, that's what Timbo will be focusing on. So you can ask if it comes up then as well.
Yeah, and I'll say to kind of give you guys an overview looking forward. So the reconstruction method that Carl mentioned and talked about in his lecture that you all just watched. Today's lab, we're going to be focusing on the equations for how we calculate how much water is in a specific point in the snowpack using reconstruction. And today's lab is doing that for a point on Earth. The next lab, we're going to be looking at how we can use MODIS satellite data combined with estimates of all the energy fluxes from other data sets to do SWE reconstruction spatially over the Himalayas. And we're going to be looking at Afghanistan, how we can do that. And from our perspective, this is the most accurate available historical data set for estimating how much snow was in the mountains each day during the melt season. Which is a really valuable tool for operational use if you want to look at various years and how wet or how dry they were. And then in the final lab, what we're going to do is we're going to use all those reconstruction data sets that we'll have experience with in the next two labs. And we'll show you how we use that reconstruction data as our training data for the machine learning models, where we can estimate how much snow is in the mountains in real time. Because one really important component of reconstruction is that we can't do reconstruction in real time. We have to wait till all the snow is gone and melted, and then we can do it backwards in time, back to the peak amount of snow. So there's a lot of it's a really powerful tool. And so in the next two labs, we're gonna go through how we do reconstruction, how we can do it spatially, ways that you could potentially do it to look at areas of interest, and then how we use it as a tool to train machine learning models to estimate SWE in real time, leveraging what we can see in real time, which is the snow-covered area from optical satellites. And that's our most reliable, one of our more reliable real-time spatially distributed measures of snow in the mountains is the covered area of the snow. So that's kind of an overview of where we're going. And I think we just had one more question come in, Carl.
Yeah, and let me just add one caveat before we move on to that question. This method is really good for areas without ephemeral snow. So if it snows and then melts in a day, and then there's no snow there for 2 weeks, and then it snows again and it melts, it's not as useful. The snow covered area will tell us if there was snow there, but the snow is not very deep. And, these sort of graphs here that show accumulation starting in November and then melting out in July with sort of, at least a few 100 millimeters of snow are sort of the places where it works best. So although it's the most accurate for sort of seasonal snowpacks, there are some benefits to using, say, passive microwave and maybe ephemeral snow areas where it just snows, a few centimeters and then goes away, and maybe that's the strength of the passive microwave.
Yeah, and another point too is like kind of how we talked about on Monday, how there's a few different methods to estimate snow water equivalent, and no one method works great everywhere. So you kind of have to understand the local area you're interested in and choose the right method. The reconstruction also works best when there's a very distinct accumulation season followed by a very distinct melt season. So you're not getting kind of snowfalls during the melt season. And it also works best when you have a melt season that's relatively cloud-free. So in Afghanistan and in the Western United States, where we do a lot of our work, you have this very distinct accumulation season where the snowpack builds up over many months, followed by a very dry melt season with low cloud cover, where the reconstruction information works really well.
And so I saw the question about doing the reconstruction in vegetated areas. And the answer is yes. I just didn't talk about it in lecture 2 because we're sort of just focusing on a point. So we'll talk more about some of these components related to under canopy or vegetated areas. You know, if you have grass or shrubs poking through, a lot of these things won't be very much different. If you have trees will block some of the solar radiation and they'll emit more long wave radiation. They'll also change the surface roughness, which has to do with the sensible and latent heat. And they'll decrease the wind speed, which has to do with the sensible and latent heat. So I'll talk more about that in lecture 3, and some of these factors as well related to like how much of the sky does that point on the ground see if there's mountains coming up on the sides of you. But also those mountains on the sides of you are emitting long wave radiation towards you. And they're also reflecting short wave radiation towards you. So it gets a bit more complicated when we move to the basin scale. And for the lecture I just gave, I wanted everyone to sort of see like, okay, if you don't need to take into account vegetation and all the surrounding terrain, it was a lot of equations anyway. So I just wanted to start there, and we'll talk more about some of these other factors in the next lecture. Oh, we got another question. What is 1 cubic meter of snow to change it to water? The amount of energy?
So we're gonna do that in the lab. So we're gonna go through kind of how much energy you is needed to change snow into water. But Carl can give like a conceptual overview right now, really quick. Or I can do it.
Go ahead, Timbo.
Yeah, so it depends on 2 things. So it depends on the temperature of the snow. So there's 2 things that need to happen to change snow, which is frozen water, into liquid water. You need to raise that snow up to 0 degrees Celsius. So the snowpack could potentially be very cold. You could have snow at -15°C. So if the snow is that cold, the first thing you have to do is you need a certain amount of energy to raise the temperature of the snow. And that's that sensible heat that Carl talks about in the lecture. So that's actually raising the temperature of the snowpack. And then the second thing you need is you need the energy that changes the phase of the water from ice to water. And so that phase change energy to go from frozen water, that's the snow, to the liquid water, that's the latent heat of fusion. So it depends on basically how cold the water is, how cold the snowpack is. But those are the 2 main components of energy. And you can see Carl has them both here on the slide, where we have basically the specific heat of ice, which is basically how much energy it takes to raise a kilogram of ice 1 degree Kelvin. And then we have the latent heat of fusion, which is how much energy it takes to convert a kilogram of ice to a kilogram of water. And one really important thing to see here is you can see that the latent heat of fusion is about 300 times more energy required than the specific heat of ice. So the amount of energy that it takes to convert frozen snow to liquid water is really high compared to the amount of energy it takes to heat the snowpack up by 1 degree Celsius. And so those are like the 2 main components there for converting it from snow to water. And we'll go into more details in the lab exercise here in a few minutes.
And for the lab, are you doing cold content, Timbo, or is that
No, in the lab, we're not doing cold content. So we're assuming an isothermal snowpack. And that's partially because for the SWE reconstructions, when we start on the date of meltout, we're assuming that the snowpack is warm and at 0 degrees C. And then we're just assuming that it stayed at 0 back to peak SWE date. So in the lab, we won't be doing the cold content calculations.
Amrit, that's a bit hard of a question to answer without understanding a bit more, like in relation to, sorry, I should read the question. Amrit asks if points out that there's an unusual spike in SWE in the ERA data set for 2015.
So I'm going to share the graph that Amrit shared in the chat right now. So you guys
Oh.
should be able to see that. Do you guys see the graph that Amrit sent out?
So I had a slide that I was going to include that basically says, know where your data is coming from, look at your data and understand it. And looking at this data, you can see every year before 2015, the peak is way smaller. And so you can sort of just use logic to throw this one out. It's hard to say what the error is. It could be, for example, that there's a no data value. Sometimes the maximum value in a data set is used as a no data value. And if you don't identify that value and remove it, you might end up with something that looks like this. Or there could just be an error with the data. So it's a little hard to say what the issue is, but the answer is, yeah, there's a problem with the data here. And I'm not sure at what step that problem is.
Yeah, that's a really good point Carl made there, where with a lot of these SNO data sets, a lot of the processing of these data streams is automated. So there's no person physically looking at every data point before the product is produced and delivered to the end users. And so with a lot of these data sets, it is really important to use your conceptual understanding to kind of gut check what you're getting. Because stuff like what Amrit pointed out here in this ERA 5 or the MERA data set, which is a big model simulation of the SWE, there are sometimes errors and problems. And so it's really important to catch those. Because with a lot of methods, we like to say if junk goes in, then junk comes out. So you want to, if you have data like this that you know isn't high quality, it's better to just not use it than to try and run whatever analysis or decision tool you're using with that bad data, because it usually won't give you informative answers. And that brings, so for that graph that Amrit shared, that was part of the lab exercise we didn't get to at the end of the last session. And for today's lab, we're going to start with the lab for today. And then depending on how much time we have at the end, I'll go back and do the rest of the lab from Monday. But that second half of the lab with the SWE reanalysis, the SWE reanalysis data sets fits in really nicely with lab 3. So if we don't have time today, I'm going to piggyback that into the lab on next Monday morning, where it fits in really well with those topics.
So I'll answer the last question here, and then I think we should get started with the lab.
Yeah.
The question is there any difference for estimation of dry and wet snow water equivalent? So for passive microwave satellites, the algorithms only work in dry snow. And let me share this graph that we've seen a few times once again. Sorry, just looking for it here. Well, I'll just say it in words. So if snow is wet, it actually emits its own signal. And when we're trying to measure the signal coming through the snowpack from the earth, that's what we're usually trying to do. The signal from the water in the snow overwhelms it. So there is a technique.
Microwave.
Yeah, for passive microwave. So for the reconstruction method, water might exist in the snowpack that's already melted, but usually that drains out. So I think not really for the reconstruction method, but yes, for passive microwave. And then for the snow extent from say MODIS or some other shortwave and infrared satellite, it might see the snow as slightly darker, but really it sees it the same way. So really it affects passive microwave observations. A lot of times you'll basically be getting, I guess that could be an answer to, no, it's not. Yeah, so water in the snowpack affects passive microwave observations, but otherwise it's not an issue.
Yeah, I'd say the only time for the optical satellites where you have water on the snow being an issue is if you have meltwater ponds on a glacier, or actually like a deep pool of water that's on the surface that is significantly darker than the snow next to it. But if the snowpack is just isothermal at 0 degrees, where you have a mix of liquid water and frozen water, the optical satellites can identify that as snow cover just as easily as dry snow. Whereas Carl said with passive microwave, it's not, we can't measure wet snow with passive microwave. Another example of it depends on your situation, which tool you use. So like passive microwave can be maybe better midwinter when you know the snowpack's really dry. And it might not be a tool you want to use, say, in June or July at the end of the season when you expect the snowpack to be ripe and wet.
So I think I'll continue to answer some questions in the chat as Timbo gets started here on the lab.
Yeah. So I am going to send everyone a link right now in the chat. You guys should have all just gotten it. And that is the link for today's lab. And I am going to fire it up also on my computer and share my screen. And we can get started with the lab exercise. So I'm just going to pull it up. And to know when everybody is ready, I have another poll that I'm going to launch right now. And basically, I just want everyone to let me know once you have the same screen up that I do. And you have today's lab loaded in your browser and ready to run. And once we have everybody with the lab loaded, we will move on to the next step and go through today's lab. And if anybody has any issues accessing the lab, please just type in the chat and we'll help you out. And it might take a few minutes for it to load. So we'll give it a few seconds.
Timbo, did you ask everyone to click on the IPNB file?
The what?
The top file on the once.
Yeah. So once it fires up, you're going to see this page right here, this Jupyter Notebook session. And this is similar to Lab 1, where all the data is in this folder. And what we want is the point energy balance model IPython notebook file. I'll circle it here. You want to click on this file. And this is the file that contains today's lab. And then all the data for today's lab is in one CSV file. And during the lab, I'll go through and explain kind of where the data came from.
So I see someone can't load the lab. Do you, is that because it's low? You could maybe put in the chat window what the issue you're seeing is. And we could go into a breakout room if we can't figure it out to maybe try to get you loaded. Timbo, do you want to, oh, I guess I can create a breakout room. So if someone's having trouble loading the lab, at the bottom of your screen for the Zoom, there's a little pattern that says breakout rooms, and you should be able to click on that, and I can join you in the room and try to help you get the lab loaded if you're having trouble.
Cool. Well, it looks like everyone else has been able to load it. So I will go ahead and get started here. So today's lab, as I said before, is a point energy balance model. So what we're doing is we're going to be solving for the energy balance at the surface of a snowpack for 1 point. And this is, as Carl said, this is our physically based approach that we like to use to model the volume of snowmelt each year. And it's how we do, it's the equations behind how we reconstruct a snowpack. Today's lab will be useful both in terms of understanding how reconstruction works, If you guys have any field stations in the mountains, or you're potentially interested in installing sensors to measure the snow, I'm going to go through and show an example. I'll show you our site that we have at our main research station in California, and all the sensors we have that we use to measure the snow to estimate how much water's in the snow. And that's where the data came from for today's lab. And so to get started, the main conceptual point for today's lab is how do we melt snow? So what we're really interested in is how much water is coming out of the snowpack. And to know that, we have to know, as we said in responding to questions earlier, well, how much energy does it take to melt a snowpack? And so the first thing we want to do in this lab is we've just laid out the equation that explains how you figure out how much energy it takes to melt an isothermal snowpack. So the first important concept for this is to understand that when we talk about energy in the lab, we're always going to be referring to energy in watts per square meter. And so watts per square meter is basically the flux of energy through a square meter of surface of Earth. And so that's a constant amount of energy that's going towards that square meter surface of Earth. And the first question in the lab, how much snow can we melt in 1 hour with a flux of 280 watts per square meter? Well, that's about if you were in the mid-latitude, so if you were in the Himalaya or in California and you went outside on a winter day or a mid-spring day in the middle of the day, that's about how much energy is going into the snowpack at noon on one of those days. So if we have about 280 watts per square meter of energy being absorbed by the snowpack over the course of an hour, how much water do we melt out of the snow? So in order to do that math, we have to know a few things about the snowpack. So this first thing is the equation to figure that out. So first we know this is how much energy we know is available to melt the snow, which is in watts per square meter, 280. And then we need to know a few things about water to know how much energy it takes to melt the water. So we need to know the density of the water, which is 1,000 kilograms per cubic meter. We need to know this next parameter, which is called the enthalpy of fusion for water. This is basically what I was talking about before. It's how much energy does it take to turn 1 kilogram of snow into 1 kilogram of water. And that is this 3.34 e to the 5 joules per kilogram. So now we have basically how dense the water is, which is in kilograms per cubic meter, how much energy it takes to turn frozen water to liquid water. And then we also need to know, well, if we're interested in how much we can melt over the course of 1 hour, this energy flux, 280 watts per square meter, that's constant. That's never ending over the course of the hour. So we need to know, well, how long are we exposing the snowpack to that energy? So we're going to be doing it in seconds, and there's 360,000 seconds in 1 hour. And then also we need to convert between meters and millimeters, and there's 1,000 millimeters in 1 meter. So the way to figure this out is what we call the melt factor. And that's basically how much snow we can melt per watt of energy available to melt the snow. And that is defined by this equation here, which has to do with how much time we have, and then how dense the water is and how much energy it takes to turn ice into water. And once we do that, if we run this equation, we press run, we can see that with a flux of 280 watts per square meter over the course of 1 hour, we melt about 3 millimeters of water in 1 hour out of the snowpack. So that's kind of a good gut check for you if you're thinking about this. If you had a sunny day at noon, later in the season, you can expect about 3 millimeters of water to melt out of the snowpack. And that's just showing you basically how much energy it takes to convert that ice into water. Does anybody have any questions at this point about this equation before we move into doing the equations for a snowpack? Okay, so now what we're going to do is we're going to apply this knowledge into doing the full energy balance of the surface for a point. So what we just did up here, this melt, that's what we're trying to figure out in all of our reconstructions is M right here. M is this flux. It's how much energy do we have available to melt the snow at any point in time. And our initial example up here, we just set it at 280 watts per square meter. Well, using station data, what we want to do is we want to be able to figure out instantaneously at every hour of the day for the entire season, how much energy do we have available to melt the snow? And in order to know that, we have to have an understanding and measurements of all the various components of the surface energy balance. And that's because the melt is driven by the flux of energy that's available to melt the snowpack. So these go back. Now what we're going to do is we're going to talk about, well, what are all these components of the energy balance equation that we need to measure that affects how fast the snow melts? So here I have it all listed out for us to go over. So there's kind of two main types of energy. The first is radiation. So for the radiation to melt the snow, we have both the shortwave radiation from the sun. So this is all the energy that the sun puts into melting the snow. And this is the radiative energy from the sun. We also need to know how we also need to know how reflective the snowpack is, which we know based on the albedo of the snowpack. And we're going to go over how we can estimate what the snowpack albedo is. We also have the long wave radiation. And for long wave radiation, we have two sources of long wave radiation. We have both long wave radiation from the atmosphere. And the main source of long wave radiation from the atmosphere that is going into the snowpack is from water vapor in the atmosphere. And then we also have long wave radiation being emitted from the snowpack itself. And that's based on the temperature of the snowpack. And we're going to go over those equations as well. And so to understand the radiative flux that's going into or out of the snowpack, which we refer to as R net, that is basically the fraction of the solar radiation that is absorbed, plus the amount of long wave radiation that's going into the snowpack from the atmosphere, minus the amount of long wave radiation that is coming out of the snowpack. And it's the combination of the solar flux and this long wave flux. You'll notice here, one important thing is that we have the long wave fluxes in our equation directly measured, but we use the S times 1 minus albedo as our solar flux. So why do you think we don't just measure the absorbed solar radiation in the snowpack? And the main reason is we really can't measure that directly very easily. So it's really difficult to actually measure how much energy is absorbed in the snowpack from the sun, but it's very easy to measure how much energy is reflected by the snowpack. And so if we know how much is reflected, we can do 1 minus the reflected amount to get at how much is actually absorbed by the snowpack. And one kind of key piece of information here that's really important for snow is really reflective. So most snow has an albedo when it's fresh and clean of 80 to 90%. And because it's so reflective, if we make small measurement errors in the albedo of the snow, those lead to far larger errors in our estimates of how much energy is absorbed by the snow. So snow albedo estimates, as we're going to see, are really important for constraining our estimate of the water in the snowpack. And so you'll see in future lectures, we're going to talk about how we can estimate the albedo of the snowpack from optical satellites like MODIS and Landsat. And all those measurements of albedo, we're estimating the albedo with the end goal of trying to estimate how much energy is actually absorbed by the snowpack. And an important point to remember is that small errors in estimates of albedo lead to bigger errors in estimates of absorbed energy in the snowpack, which lead to errors in estimates of how much water is in the snowpack. So in addition to these radiative fluxes, which is both the solar flux and the long wave flux, we then also have these sensible and latent heat fluxes that are going into or out of the snowpack as well. And these we briefly talked about for a second, where the sensible heat flux is basically a flux that raises the temperature of the snowpack or lowers the temperature of the snowpack. So you can think of sensible heat as if you're heating water up in a kettle. So if you put a kettle on the stove, the water is going to start at a cold temperature and go up to a much warmer temperature. That's a sensible heat exchange. And the second type of heat exchange in the energy flux we care about is this latent heat flux. And that's the actual phase change of that liquid, either from a liquid to a gas, from a gas to a liquid, from a liquid to a solid, from a solid to a liquid. And that latent heat flux, in the analogy to boiling to a kettle on the stove, that's similar to boiling the water in the kettle. We're actually that phase change of changing the phase of the water. And so we need to account for any latent heat fluxes that are occurring at the surface of the snowpack as well. The last flux, which Carl mentioned in his lecture, is this heat flow in or out of the snowpack. And we're going to just assume for our purposes that this heat flow is negligible. And that's because over the course of a day, this generally balances out to be equal to 0, where about the same amount of heat flows in and out of the pack. And so by setting it equal to 0, we can solve these equations and we don't have to worry about that term. And so now we get down to the main equations that we use for doing our reconstructions and estimating melt. Let's see here, okay. And that's right here where M, the energy we have available to melt, is going to be equal to the net flux of radiation, both the solar and the long wave flux, plus any sensible heat flux on the surface and any latent heat flux on the surface. And because G is equal to 0, we basically can set our equation equal to this. And this is our main equation for figuring out how much energy do we have available at any time step to estimate the melt in the snowpack. And because we're only concerned with melting the snowpack, we only care about when this value is positive. So that's what we have down here in this next equation, where actually the energy we have available to melt is never going to be less than 0. If the flux of energy into the snowpack is negative, then the snowpack is not melting. And so we're not going to be calculating any melt at that time step. So that's what this equation right here shows that I'm circling right now. We basically want to, based on measurements at our station, at any time step, we want to know what is the maximum? Do we have energy available to melt? Or if it's negative, there's no melt occurring. So at this point, now that we have this main equation, what we're going to do is we're going to go and use data from a station that we manage. And we have sensors that measure all of these components of the energy balance. And we're going to use measurements from that station to estimate for each time step how much energy we have available to melt the snowpack. And then we're going to back calculate over the course of many months when we add up over every hour how much energy we had to melt the snow, how much snow had to have been there for it to disappear on that day and melt out. So for this next part, I'm going to give you guys a brief overview of where this data set comes from that we're using. This will be really useful information to both understand how we can measure all the parts of the energy balance at a point to validate and prove that this reconstruction method works. And this will also probably be really useful information for any of you if you have interest in having surface station data potentially in the future at a location where you might want to measure properties of the snow. So we work at this location here, and we have this thing called the Snow Science Laboratory. So this is a link that is in the lab that you guys can go to. And this picture on my screen, which you guys can see, this is our station where we measure all the properties of the energy balance for the snow. And so what I'm going to do is I'm going to go through and explain to you guys how we can measure this long wave radiation, the short wave radiation, and these sensible and latent heat exchanges at our station. So this is a picture of the station in the mountains in the summertime. So clearly there's no snow here. But does everyone see this black platform up at the top? At our station, this platform is, do you know how high above the ground this is, Carl? I think it's 3 meters. Oh, you're muted.
Sorry, the platform off the ground, Timbo?
Yeah, I think it's 3 meters, or Ned could chime in if he's still on.
I think it's actually more like 6 meters. It's pretty.
Okay. Yeah, I think it's a 6 meter platform off the ground. And in a big snow year, the snow level comes up to the top of this platform. So that's why it's so high off the ground. And then this box down here, this is a big storage container. All of our computers and data loggers are inside of this storage container. And so the measurements we take here to help estimate the properties of the snow, the first one is this, what we talked about, this shortwave energy flux. And we measure that right here. So if you guys see this, this is a long boom, a long aluminum boom that is actually on a pivot, and we can raise it and lower it. So it's always just a few feet above the surface of the snow. And on the end of the boom, we have 2 instruments. We have 2 radiometers. Radiometers are instruments that measure the shortwave radiation, the volume of shortwave radiation, the flux of shortwave radiation that they see. And we have one radiometer that's pointing up, and we have another radiometer that's pointing straight down. And we're going to have the data streams from these 2 instruments in our lab. So the radiometer that's pointing up, what do you guys think that that measures? If you guys could write it in the chat box, we can see if you can guess what this measures shortwave radiation. And if it's pointing up, what is it going to be measuring? Yep, Martin's right. The incoming shortwave radiation. And then the same radiometer that we have that's pointing straight down, what is that one going to be measuring? Yep, the outgoing. So the reflected radiation off the surface of the snowpack. And this goes to where I said before, we can't actually measure how much energy is absorbed by the snowpack, but we can measure how much energy is coming into the snowpack and how much energy is being reflected off of the snowpack. And when we subtract these 2 measurements, we end up with a difference, and that's the amount of energy that was absorbed by the snowpack. So this is our tool we use here to measure that. And we're going to see the data streams from these 2 instruments in the lab. And the reason it's on this boom right here is that these radiometers are very sensitive to vegetation and other surfaces other than snow nearby. And so we want to be sure that we keep them really close to the surface of the snowpack so that they're only measuring the reflectance off the snow and that there's no signal from the trees nearby. A simpler way to set this kind of station up is to have it fixed at a fixed location far away from trees. So that's where we measure the shortwave radiation. And then for long wave radiation, we measure that over here. So if you see this pole, we have a bunch more radiometers over here. And we have one of them that measures long wave radiation. And then we have a few more that it's summertime right now, so they're not fully set up. We have another boom over here that has more radiometers on it. And some of these are measure in the long wave part of the spectrum. And so we have those looking up, and they measure the incoming long wave radiation. And then for the outgoing long wave radiation of the snowpack, we actually don't measure that directly. In the lab, we're going to show how if you know the temperature of the snow, which we measure independently with a laser beam, we can use that information to estimate the long wave emission of the snowpack. Because the amount of long wave radiation that a surface emits is directly proportional to the temperature of that surface. And so I don't know if you can see it on here. Yeah, so right here, we have a laser that measures both the snow depth. It points down this way. This laser measures the snow depth and the temperature of the snow. And we can use that temperature measurement to estimate the emissivity of the temperature of the snowpack. So that's how we measure the radiative components of the energy balance. Now to do sensible and latent heat components, we actually don't measure those directly. We're going to show you in the lab the equations that are used. But the main things we need to know for both latent heat exchange and sensible heat exchange is we need to know the temperature of the surface. We need to know the temperature of the air. We need to know the vapor pressure at the surface, the vapor pressure in the air, and the wind speed. So we have this laser beam here, which we can use to measure the temperature at the surface. What do you guys think the vapor pressure is at the surface of snow? Do you think we need to measure that? Or do you think we might know what that is, given that we have a deep snowpack? So we have one guess so far of 0. It's not 0. So
I think we can derive it using 0 degrees Celsius temperature.
yeah, we can derive the total amount based on the temperature. And then we also know, I guess a better way to frame it, what do you think the relative humidity of the air is inside of the snowpack? Oh, Carl, you're muted.
As a reminder, the relative humidity is the percent of the pore space that is filled with water, or that of the air that has water in it.
Do you wanna let him know, Carl?
I was actually reading something else, Timbo. I'm
Oh,
sorry, I missed it.
cool.
You were asking, my guess is going to be the same as the air temperature, but I might have missed what you were talking.
Yeah, we can basically calculate it right at the surface based on the knowledge that we're in the snowpack itself. And we know, yeah, so. Whereas when we have up on the tower up here, we have a sensor that is right here that measures the temperature and the humidity, and we can get the vapor pressure up at a point far above the surface. And then the last component that we need for these sensible and latent heat fluxes is the wind speed, basically above the surface of the snow. And we have two ways we measure it here. We have a sonic anemometer, which is this instrument, which based on pinging sound waves from 3 different positions, we can calculate the X, Y, and Z direction of the wind. And then we have a more traditional wind vane right here that also can measure wind speed and direction. And so based on knowing the temperature and the humidity at the surface and at a point above the surface and the wind speed, we can use that information to understand those sensible and latent heat fluxes. So those are the main tools that we use for doing the energy balance. Before we move on, just a few other kind of important measurements you can make of the snow that might be of interest to some of you before we leave this figure. We also have at our site these boxes over here. You guys can maybe see these. These are stainless steel pans in the surface. Hold on one sec. Let's see if I can zoom in. Okay. So we have, these are lysimeters, these stainless steel pans. So this is where we can actually directly collect all the meltwater out of the snowpack. This is a way to independently validate if our reconstruction approaches work. We also have at our site, these are LiDARs. So this is a way we can measure the surface of the snow at really high resolution, the topography of the snow, see how deep it is, see how it varies over time. And then another cool instrument we have is this over here, which is called a Parseval, which is a band of laser beams that as snowflakes fall, it actually measures each individual snowflake. And we can get the shape and size of the snowflake. And depending on how many snowflakes fall through the band of laser beams, we can get a really direct estimate of the snowfall rate. So those are some of the tools that we use at our site to measure the snow. And if anybody has any questions about that, or if anyone we're happy to answer any questions about decisions you might make to use to take measurements of the snow at a surface site. So now that we've done that, we're going to go ahead and do the lab exercise. So I'm going to clear my annotations. Let's see.
Timbo, just a heads up that you might need to explain restarting the kernel for some folks.
Oh yeah, okay.
Mine died while we were waiting.
So now we're done with that. We're going to go back to here. So if your kernel has died on your Python session, just click try restarting now, and it should fire right back up. If it doesn't, just re-click on the link in the chat and it'll fire your lab back up.
You can also go to the menu that says kernel and do clear.
Yeah, so right here you can do kernel and you can do restart and clear output. And that should load you back up. So now to run the reconstructions, we want to load up all this data into our Python session. So to do this lab, we're going to be using the following libraries. So we'll be using pandas, NumPy, and matplotlib. And then we're going to load those up and then load in the data, which is this CSV file here. And really quickly, just to show you, the data for this lab came from our website here, and this is our data. We have this model ready data, and we have all of the data sets needed to run the lab. So you guys are welcome to click on these links on your own time and explore. And if you have any questions, feel free to ask us. So we will load up the data into the lab. And when we load up the CSV file, we can see what data we have and what measurements we have from the field station. So this is a visualization of the first 5 rows of the data frame. If you remember from the last lab, a data frame is a table in Python. So this is a way that Python stores the data so that we can manipulate it and do equations on it. So for each row, we have a bunch of data for a certain time point. So we have the time that the data was acquired. The first timestamp in our data set is in September. And at our station, there's usually no snow at September. So you'll see at first that there's lots of zeros, but that's okay. This is just because we're recording at the station prior to any snowfall. So we have the timestamp. You can see we have a recording every hour. So we're going to be looking every hour at the energy balance to do our reconstructions. We have data from this uplooking broadband radiometer. We have this uplooking direct. This takes the direct beam radiation from the sun. And this has the uplooking diffuse. So this is the diffuse radiation from the sun. These two measurements are the same if you add them together as this measurement over here. So sometimes we might be interested in how much energy is coming directly from the beam of radiation from the sun versus the diffuse radiation that's being scattered towards the surface. We also have the uplooking shortwave radiation. We have the snow albedo. The snow albedo is calculated from those two measurements, those two radiometers that I told you about on the end of that boom. We also have the uplooking long wave radiometer. We also have the wind speed at our station in meters per second. This is the wind speed on the platform, which I think we told you was about 6 meters above the surface of the ground. And we'll see that in the lab also. We also have the direction of the wind. We have the tool that was used to measure it. We have the air temperature on that platform. We have the relative humidity on the platform. We have the air pressure on the platform. And then we also have the snow depth on the platform. And the snow depth, as you can see right now, is 0. There's no snow yet that season. In addition to the snow depth, we have the SWE measured in centimeters. And this is from a snow pillow that we have at the site, which Carl mentioned snow pillows in his lectures. It's like a big scale in the ground that measures the weight of the snow above it over about a 5 by 5 meter area. And so we're going to use this measurement of snow water equivalent as an independent way to verify that we can use all these other measurements to calculate how much water's in the snow with reconstruction. So these are all our data points we have from the station. Just a quick thing here. So this command head is what displayed the first 5 rows. If we want to see more, I could type, let's say 100 right here and click run. And now we will see 100 rows of data. And you can see it shows you the first 5 and the last 5. The middle chunk is appended right here. And you can explore how much of the data set you want to look at. So now let's look at let's visualize this data. So first, what we want to look at is we want to look at the snow depth and the snow water equivalent and see how much data we have here in this data set. So if you guys will click run on this line here where we have ebdata.plot, we can plot the snow depth and the snow water equivalent. So here are the hourly readings of both snow depth and SWE at our station. So from here we can see we have 5 years of data. And we can also see that we have this really expected cycle of winter snow and summer there's no snow there. And we can also see, do you guys notice any difference between the snow depth and the snow water equivalent lines? Do they look, do one of them look potentially a lot smoother than the other one? Why do you think the snow depth line is a lot spikier, a lot more jagged than the snow water equivalent line?
What's the missing variable here? So there's snow depth, and what else do you need to get to the SWE? There it is.
Yep, both of you guys just got it, the density. Yeah, so the SWE is both the depth times the density. And from these really jagged lines, you can see that the snow density is not the same throughout the year. And generally when the snow first falls, it's pretty light and fluffy, and it can be very light and not so dense. And so we can actually see a lot of individual storm events that occurred throughout the year, each year, where we basically have a snow event where the depth goes up quite a bit. And then in the week or the day or so after the snow event, the snow depth actually declines quite a bit. And that's from the snow just settling and densifying and compacting. And so that's kind of cool that you can actually see that in these measurements. And that's a really important thing to remember, is that depth times density equals SWE. We can also see here that it's pretty variable. So the Sierra Nevada is similar, has really wide range of annual amounts of snowfall that we get. So this is where kind of that SWE climatology that we've been talking about a bit comes into play, where you can see here in 2015, we had about 1/5 as much water as we had in 2017. So this dry year is almost an order of magnitude less water than we have in this wet year in 2017. And this is one of the really important reasons it can be to need to have really good estimates of your snow water equivalent each year, is because the amount of water that's in the snow can vary dramatically from year to year and place to place. So now what we're going to do is we are going to pick a year to look at data, and we're going to try and estimate the snow water equivalent for that year. So to do that, we're going to first look at the measurements of the solar flux at our site to understand the solar flux component of the energy balance. So remember what we talked about, that the solar flux into the snowpack, the amount of solar energy absorbed by the snowpack, is going to be equal to basically, we can't measure it, but it's going to be equal to the amount of incoming solar radiation minus the amount of reflected solar radiation. So what we can do is we can basically calculate reflected solar. And that is going to be based on basically how much we measured coming in, how much shortwave radiation was coming into the snowpack, which is this variable here. And we can multiply that by the snow albedo that we have at the site. And that will give us the total amount of reflected solar radiation. And when we look at that, we can see these two measurements. So the blue line is the solar radiation hitting the surface, and the orange line is the amount of energy that was reflected off of the snowpack. So first question is, which Do you notice any difference between each of these days? Do each of these days look the same, or are some of the lines a little different than the other ones? Like, for example, this last day here, let's see. This last day here is much smaller. And this day here also looks very different with these jagged spikes in it. Whereas this day over here is a perfectly smooth line, perfectly smooth. Why do you guys think these 3 days are different? Does anybody have any ideas for what might be causing the shortwave radiation to look differently on 3 different days when the sun is
Maybe
not
because of clouds?
Yep, that's right, Amrit. Yeah, so clouds. So this first day here, this is a really sunny day. There's no clouds all day long. We have this perfect sinusoidal shape to the radiation coming into the snowpack. Whereas we can see on some of these other days, we have signals where there were probably some clouds that came in and affected the energy. And when there's cloud cover, that scatters and reflects some of the shortwave radiation and generally reduces the amount of shortwave radiation that hits the surface of the Earth. If it's a fully overcast day, no direct beam solar radiation, it's about the same amount of radiation hitting the surface as if the sun was at 55 degrees. So this is important. This also shows you how the dynamics of how much snow melts really depends each day, can depend on if it's cloudy or not too, because it affects the shortwave radiation. And as we'll see longer, it also affects some other components of the energy balance. Can you guys think of what else might be affected by cloud cover? What other components of the energy balance might change if there's a lot of cloud cover? So one thing, the clouds, what are clouds made of? They're water vapor. So that water vapor in the clouds, it has a temperature, right? So all the clouds in the sky, they have a certain temperature to them. And based on the temperature of the clouds, they are also going to be emitting long wave radiation. And so depending on the type of cloud cover you have over your snowpack, and if those clouds are there in the daytime or in the nighttime, there can actually be additional long wave radiation that's emitted and it warms up and heats the snowpack. So cloud cover can have an impact on a few different components of the energy balance of the snowpack. Okay, so those are the shortwave fluxes. So now that we have both the total energy hitting the snowpack and the total amount of energy reflecting off the snowpack, we can calculate what we're interested in, which is how much energy is absorbed by the snowpack. And we're going to call that the net solar radiation. And our next plot is going to show over the same period what happens when we do that. So this graph here is now the difference from the graph above of the uplooking broadband, the solar radiation hitting the snowpack minus the solar radiation reflected off the snowpack. And this gives us the graph that shows us the net flux of solar radiation being absorbed by the snowpack. You can see up here that we're now in that range where we were doing our initial guesstimate of 280 watts per meter squared from the first part of the lab. We can see on a clear sunny day in the spring, there's about 340 watts per meter squared hitting the snowpack. And on a really cloudy day, that drops down quite a bit to a little less. So now with this graph, we have that solar component of our radiation balance for these days. So let's go on and now look at the long wave flux. So the long wave flux has two components. We have basically the emission of long wave radiation from the snowpack. So that's going to be energy leaving the snowpack. And then we have long wave radiation from the atmosphere being absorbed by the snowpack. And so first what we're going to do is we're going to look at the long wave flux that is being emitted from the snowpack. And this equation right here is the equation for long wave radiation. And for snow, it's basically the long wave emission, the radiation emitted from the surface, is equal to the emissivity of that surface times a constant called the Stefan-Boltzmann constant times the temperature of that surface to the 4th power. So like I said before, we don't actually directly measure the long wave emission off the surface of the snow, but because we measure the snow temperature, and we also know the emissivity of snow, that's a constant. Snow basically emits all the same amount of energy that it absorbs. It has an emissivity of 0.99. So because we know its emissivity and we know its temperature, we can calculate how much long wave radiation is being emitted by the snow at any point in time. And then to figure out the long wave radiation coming out of the atmosphere, we have an upward looking radiometer that measures that. And that long wave radiation from the atmosphere is dependent on the temperature of the atmosphere, which a lot of that is influenced by how much water vapor is in the atmosphere, with clouds being an example of if you have really warm clouds over the snow, that'll add a lot of long wave radiation being absorbed by the snowpack. And I just want to point out too, at the same time while I'm going through this lab with you guys, Carl has been actively answering questions in the chat. So feel free to look over there also and listen. And if you have any questions, you can either type them in there or feel free to interrupt me at any point in time. So with this long wave radiation equation, we can see here now in this next code block that what we do is we take all this information where we take the temperature of the snow, we take the long wave radiation, and we can calculate basically what it is going to be at the snow surface based on the Stefan-Boltzmann constant, the temperature of the snow surface, and taking that to the 4th power. So when we do that calculation and then we plot it, we can see right here. So we have this orange line, which is the amount of energy being emitted by the snowpack. So that is the outgoing long wave radiation. And then we have the blue line, which is the total amount of energy in the long wave part of the spectrum that is being absorbed by the snowpack, that is hitting the snowpack. So why do you guys think possibly that this outgoing long wave radiation is so constant across many days in May at our site? Why is this line so smooth with no fluctuation? Knowing that, let's see over here. This is the equation that was used.
Maybe the temperature of snow surface is nearly constant.
Yep. And why might the temperature of the snow surface be so constant in this late in the spring?
Because maybe the maximum temperature that snow surface can reach is around 0 degree. Yeah, 0 degrees Celsius.
Yep, that's exactly right, Amrit. So we have here is a ripe snowpack, an isothermal snowpack, where this is late enough in the season when we're looking at these days that the snow is just already at 0 degrees C and it's not fluctuating at all. If we were to, let's see if this should work. If we change the dates that we're looking at, so right now we're looking at a week in May. If I change this to a week in January, so now we're basically querying these dates. So January 1st to January 7th instead of May 1st to May 7th. If I rerun this plot, now you'll see that the snow surface actually is different. So that orange line now actually varies quite a bit. And that's because in the middle of winter, the snow can actually be much lower than 0 degrees C. And that has what Carl was talking about in his lectures, how the cold content of the snowpack. First, we have to raise the snowpack from whatever temperature it's at to 0, and then we can start melting the snow. So when we go back here to this week in May and we run it, you can see that, yeah, we have this isothermal snowpack. So feel free if you want, you can query any dates that you want across the time period of record for our measurements, and you could look at other weeks and see what the long wave emission was of the snowpack during that week. So now that we have both of these components, we have the long wave radiation coming into the snowpack, we have the long wave radiation being emitted from the snowpack. We can figure out the net flux of long wave radiation, the net long wave, which is what we're interested in for the energy balance, which is basically the total amount that's coming down towards the snowpack minus the amount of energy that's leaving the snowpack. So when we do that equation and we plot it, we get this graph. And this is showing us when we balance out all the long wave radiation, this is the net flux of long wave radiation at the surface of the snowpack at each hour over the 7-day period. So let's see. Now what we want to do, let's look at both. We've done 2 of the 4 components of the energy balance. We've done the net flux of solar radiation and the net flux of long wave. And if we plot both of those next to each other, we notice some interesting things. So why is the net solar flat line at 0 over and over and over again? These parts of the graph right here. Why are those so flat and at 0?
And as a reminder, on the x-axis, you can see the 1st of May, the 2nd of May, the 3rd of May, all the way up to the 7th of May. So you have a few days here.
Yeah, and Wangchuk Namge just in the chat box said that it was nighttime. And that's correct. So there's no solar radiation at these time periods. So it kind of goes to 0. It does go to 0 because there's no energy input. Now, what about the long wave radiation? This looks really different. So the long wave radiation, it looks like it's always negative. And so what does that mean if the net long wave radiation is negative? Is long wave radiation, is it causing the snowpack to melt, or what's going on right there? Remember, this is late in May. This is even in the melt season when it's pretty warm outside. What do we understand by knowing that it's a negative? We have negative values for these long wave radiation values.
And you can think about what the sun's doing, the blue line, right? And those are positive. So if the sun, is it heating? Is the sun heating or cooling the snowpack?
If above 0, then that should be heating. And if the net long wave is negative, then the snow surface is cooling.
Yep, that's correct. Yeah, and so it's interesting that the long wave radiation is actually cooling the snowpack off. So it's actually not a net driver of melting the snowpack. And when we go back up and look at our long wave, we can see that basically the snow surface is so cold that it's actually emitting more energy than is coming in from the emission of long wave radiation from the atmosphere above it. But one interesting thing you can also see is, do you guys remember, what did we decide was happening here on this day with this jagged peak in the net solar and this day right here? Do you guys remember why we saw that? So those were cloudy days. And it's interesting, on the cloudy days, I also mentioned that clouds and the water vapor in the clouds can increase the amount of long wave radiation that is emitted from the atmosphere. And you can see on these 2 cloudy days, the net flux of long wave radiation actually gets much closer to 0 and almost crosses it too. And you can even see here at night, this is interesting right here, where you actually get, and over here too, the long wave radiation almost goes positive. And why, the most probable reason for why this is happening here is that this is time periods at night when there's probably pretty extensive cloud cover, and those clouds are pretty warm. And so the emissivity of long wave radiation from those clouds are actually driving that net flux of long wave radiation towards the positive in the snowpack. So a really cool part of this energy balance modeling is thinking through the physical reasons for the different signals that you see and getting an understanding of what might be going on over the snowpack in those areas. So now that we have done let's clear the drawings, close that. So now we've got, does anybody have any questions about the long wave radiation flux or the short wave radiation flux before we move on to sensible and latent heat fluxes? Okay. So now what we're going to do is we're going to go talk about the sensible heat flux. And so if you remember, and Carl talked about sensible and latent heat flux in his lectures, but the sensible heat flux, we don't actually have a sensor on the station. There isn't a sensor that can directly measure it. What we basically need to do is we can measure a bunch of other properties of the environment and use that to calculate the sensible heat flux. And so this is the equation for the sensible heat flux up here, where we take the density of the air, the specific heat of the air, the difference between the temperature of the air and the temperature of our surface, which in our case is snow, and then this term that we call it's the aerodynamic resistance over the snow adjusted for instability. And there's lots of ways you can estimate sensible and latent heat flux. They can get pretty complicated. For everyone today, the really important thing I want everyone to remember is that for sensible heat flux, what it's driven by is a temperature difference between the surface and the air above it, and then also how much mixing you have above the surface. So the greater the difference in the temperature between the surface and the air above it, more sensible heat flux. The more mixing that you have above the surface, the more sensible heat flux. And if you have both a really big temperature difference and a lot of mixing, you're going to have a lot of sensible heat flux. And what might cause mixing in the mountains right above the surface?
Yeah, that is wind.
Yep, that is the wind. The wind is the main driver of that mixing. And this can get really complicated depending on the terrain, if there's trees and vegetation or not. And so lots of people spend a lot of time figuring out how best to parameterize their estimates of these fluxes based on the knowledge of the mixing, which is due to that wind. So what we have here now is I have all of the constants that we need to calculate the sensible heat flux, along with all of the measurements we need at our station to also estimate the sensible heat flux. So up here first, we have all the constants that we need for our equation. To give you, this is the specific heat of the air. This is a constant that's needed for the sensible heat equation. All of these go into basically what I was talking about with kind of this understanding of how stable and how rough the surface is for causing the mixing. In addition to these constants, we have the measurements at our station that are really important. So like I said, we need to know the temperature of our surface and the temperature of the air above our surface. So right here we have our snow surface temperature that I said we measure at the site. And then we also have the air temperature. And an important thing with the air temperature that we need to know is we actually need to know where we measured that air temperature. So we need to know how high above the surface that temperature measurement is. Because basically if we take a temperature, let's say we have the snow is at 0 degrees C and the air is at 10 degrees C. If the air is 10 degrees C, 1 meter above the surface of the snow, That's a much bigger temperature difference than if the air is 10 degrees C, 10 meters above the surface of the snow. So that distance between the two measurements is really important. We also have the wind speed. And this is that height right here, basically, the ZR, is we can figure out how high above the surface the wind speed measurement is. And then we also have the air pressure at the time of the measurement as well, which we can use to find the density of the air. And then these are all equations that are, we don't really need to go into the specific details of them, but this is how you parameterize and calculate if the air is stable or unstable above the snow surface, and then what the sensible heat flux is. So when we run this, we calculate our sensible heat flux. So what we want to do now is I want to look at, basically, we used a few different measurements to get to the sensible heat flux. So I want to look at those and plot some of them. So the first one we're going to plot is this wind speed measurement height. And that's ZR. And so this is for over the full period of time that we have measurements for, these 5 years. We're looking at the height that we're measuring the wind speed. So why is this changing so much? Why is our wind speed height? Are we moving our wind speed sensor around on our station every day? Why is it changing so dramatically?
I think the sun is like uneven heating of the surface, making the change this wind speed.
So the wind speed is changing a lot.
Uneven heating by the sun is making like over the during the day.
Yes.
Making the speed of the wind to change over the time.
Yep. So the wind speed is changing a ton. This is a measurement of the height above the surface that we're measuring the wind speed. So if we wanted to look at the actual wind speed, we could do this. This is our measurement of the wind speed. And let's see, U. So U is our variable that is wind speed. So this is wind speed. So there you can see the wind speed. It moves around a lot. But what we were looking at before was actually the height above the surface that we were measuring the wind speed, which is this graph. So why do you guys think the height at which we're measuring the wind speed is changing so much? And remember, when we're thinking about this, what we care about is, for the sensible heat flux, the temperature at our surface, and then the temperature at a specific height above that surface, and the wind speed at a specific height above that surface. What is the surface in our model that we're measuring? Is it the ground or is it the snow? The snow, right? That's right, Waleed. So it's the snow surface that we care about. And the snow surface is changing every day. As it snows more and it gets deeper, as the snow compacts and melts and it gets shallower. And so what this is looking at, the reason this wind speed height measurement is changing all the time is we're actually accounting for the fact that the snow depth is changing. And so the difference, our wind speed measurement device is always at the same spot, 6 meters above the bare ground, which is why you can see in these flat parts here, when there's no snow, the wind speed measurement height is constant. But during the snow season, we can see that the wind speed measurement height decreases because the snow depth increases. And so we really want to track the difference between our measurement height and the snow height. And so that's really important too, because it really affects our results. So now what we can do if we want is we can look at any other variable that we have here. So let's say we want to look at the air temperature. We can take that variable, the air temperature variable, we can plug it in here. And we could also look. So go ahead and in your guys' lab sessions, you can click around and plot any of the variables that are used to measure sensible heat. And you can run the graph for them. So here we can see the air temperature over this 5-year period, where we have this really distinct long-term signal of kind of the summers and the winters, but then a whole bunch of variability day to day with the maximum and the minimum air temperatures. So if everyone wants to take a sec and pick another one of these measurements here and plot it up in your lab. I'll do one more. I'll do while you guys are doing that, I'll pick another one. I'll look at the snow surface temperature over this 5-year period really quick. TS. So here's our snow surface temperature measurements. And here we can really see in the winter time. So 0, this is all Kelvin on the y-axis. So 0 degrees C is right about here. We can see that some of our minimum snow surface temperatures can be up to 20 degrees colder, 20 degrees below freezing, which is pretty amazing. So now that we've looked at some of the different variables that go into calculating that sensible heat flux, what we did up here is we actually calculated our sensible heat flux, which has to do with some constants, which is the density of the air and how stable the atmosphere is, how the wind and the mixing is that is occurring above the surface, and then that temperature difference we have right here between the temperature at the surface and the temperature of the air. And we can plot what the sensible heat flux looks like for that same 5-day period that we were looking at before. And so what do you guys notice about this compared to those other long wave and short wave fluxes that we looked at? Does the sensible heat flux look as regular as those other ones? There's no kind of distinct pattern that we saw. Like if I go up here, here's the net long wave and short wave. We really saw this consistent repeated pattern day after day with these measurements. But down with the sensible heat flux, it's really not quite as, it's not the same. And a lot of that has to do with this really is driven by wind and temperature, and wind and temperature don't correlate as directly with time of day as solar radiation does. Solar radiation is very, very predictable, but this is much more of a local condition that can change from time to time. So again, here, if we pick another, let's go to another week. Let's look at, say, the first week of February instead of May. And if we look here and we plot the graph, we can see again that it's very different. And what you also notice here is we actually have a few days where there's no sensible heat flux. Why might you think that we're not getting any sensible heat flux? Why would it go to 0? What could be happening at that point in time? Remember I said that when we calculated sensible heat flux up here, this was really important. We had to have a temperature difference between the air and the snow. So if it's at 0 here, what that means is there is no temperature difference. So if there's no wind, if there's light wind, if it's really calm, and the air temperature is the same as the snow temperature, you're not going to get any sensible heat exchange. And if there's no wind and no mixing, the thin layer of air that's right above the snowpack will come to equilibrium with the snow below it. And you'll end up with basically no heat exchange between those two. And we can see that right here. If we go to another week, say we go to the first week of January, we can see here too, we had really little sensible heat flux. But if we go back to May, we can see that we have a lot more variability on each hour of the day. So now, does anybody have any questions about sensible heat before we go to the last component, the latent heat flux, before we do the reconstruction of the SWE? So for latent heat flux, it's really similar to the sensible heat flux in that we're looking at, in this bold down here, it's driven by a difference between the surface and the air above it and how much mixing is occurring. For sensible heat flux, it was all about the temperature difference. We wanted to know how warm the air was and how warm the snow was, and the difference in those temperatures, because we were raising the temperature of the snowpack or lowering the temperature of the snowpack. For the latent heat flux, it's all about the vapor pressure differences. So it's both how much mixing is there, and then it's the vapor pressure difference between the surface and the air above it. And that's because it's that vapor pressure gradient that really drives the latent heat exchange and the ability of the snowpack to evaporate. So for snow to go from frozen snow or liquid water in the snowpack and evaporate into the atmosphere above it, or for there to be condensation on the snowpack and to get, it's called surface hoar, is the type of surface that we get on the snow, where you might have condensation of water vapor out of the atmosphere and onto the snowpack. And so those latent heat processes, the changing of water of phases from a liquid to a gas, from a gas to a solid, from a solid to a gas, those are driven by these vapor pressure gradient differences, vapor pressure gradients, the differences in vapor pressure between the surface of the snow and the air right above it. And so that's what's really important in this latent heat equation, is knowing how much mixing is going on, how windy is it, and then knowing what the vapor pressure difference is between the snow and the air above it. And so to do this, we can reuse, we already calculated the temperature of the surface of the snow. We already calculated the temperature of the air, and these other constants. And now what we have is we need to know basically how much energy it takes to sublimate snow. So that is to take frozen water and turn it into water vapor, which is right here. And we also need to know the latent heat of vaporization, which is how much energy does it take to take liquid water and turn liquid water into water vapor. And you can see here, it takes more energy to take a solid and turn it to a vapor than it takes to turn a liquid to a vapor. Once we have all that, what we need to do is we have to calculate the vapor pressure of the air. I've added a reference here, which the link to this reference is actually up. Sorry about this. It is right here. So if you guys want to look more closely into these equations, you can click on that link. But where are we? Okay, latent heat flux. These are the equations that we use to calculate basically what the vapor pressure is. And for the vapor pressure of the surface, so the vapor pressure of the snow, we can calculate, where is it? It is right here. So you guys can, I think for this, there's more details here than we have time to cover in the next 10 minutes. So I think the best would be if you guys care about the specific details of this latent heat calculation, to do this lab, go through each equation, and then we can talk about it at the start of the next time. But to get to the reconstruction stuff, I think the most important concept to get from this set of equations is that we're calculating the vapor pressure in the air, the vapor pressure at the snow surface, and how much mixing is going on. And from that, we can calculate this latent heat flux right here. And to look at it, let's see, run this. So this shows you, this is the temperature above the snowpack, but what we care about is this next plot, which is This is the latent heat flux at the surface of the snowpack over this 5-day period in May. And we can see here that it goes both from negative and positive values. So if it's negative, that means that, what does that mean? Does that mean that we have water vapor being deposited on the snowpack, or does it mean that we have snow sublimating off the snowpack? So feel free to write in the chat box if you think you know. So if energy is leaving the snowpack from latent heat exchange, what that means is that you have energy leaving it.
Which is similar to what we saw with the long wave, right, Timbo?
Yeah. So if the energy is leaving it, we have basically sublimation occurring, where we have energy that was in this, that we have energy that was going into from the snowpack that is now in the atmosphere. So that liquid, that solid or liquid water that's in the top of the snowpack, it's gone to a higher energy state in the atmosphere, and we have negative latent heat flux. Okay, so now that we've done all the different components of the energy balance, let's plot all of them on top of each other and see how they all relate to one another. So these are all 4 of the different components we talked about. So we have the latent heat flux, the sensible heat flux, the net solar, and the net long wave. And then the blue line we have here shows when we basically add them all together at any point in time, how much energy is either going into or out of the snowpack. And this is really interesting. So we can see this comes back and touches on all the different parts of what we talked about so far, where we can see the solar radiation each day, we can see the long wave down below, and we can see kind of, as Carl mentioned in his lecture slides, during the daytime, solar radiation really drives the energy that's going into the snowpack. Each day we can see that there's a lot of positive net flux of energy going into melting the snow. And then at night, it kind of dips down to the negative, and we can see the snowpack cooling most nights. But on some nights, it doesn't actually cool all the way. Like right here, for example, we can see periods of time when the net flux is still positive. And a lot of that has to do with the long wave radiation balance, and the sensible and latent heat exchanges, which we can see here are positive due to high wind speeds and big temperature and vapor pressure differences that are driving energy into the snowpack and causing it to melt. Gesundheit.
Thank you.
Okay, so now that we have all this, what we're going to use to do our reconstruction is this net flux variable right here. And if we're interested in melting the snowpack, do we want to always, we don't want to always use this net flux variable, because at these periods of time, our net flux is negative. We're not actually melting the snowpack. So the energy that's available to melt is actually this right here. It's the maximum of our net flux or 0. So if net flux drops below 0 and the snowpack is actually cooling, we're not melting the snowpack. And so if we're not melting the snowpack, we don't want to drive our reconstruction with those data points. So this next graph, what we're going to do is it shows just that. This shows the net flux only when it's above 0. So this is each day how much energy is available each hour to melt the snowpack. And you can see it peaks out right about at that 280 watts per meter squared, which is what I said. If you go out on a spring day to a snowpack around noon, it's sunny and clear, it's probably about 280 watts per meter squared of energy going into that snowpack at a mid-latitude elevation. And so how the reconstruction works is what we really wanted is this right here. This graph is kind of the secret sauce for how we can drive a SWE reconstruction. From all these energy balance components, we now know at each hour of the day how much energy is going into that snowpack. We also know from the very beginning of the lab how much energy it takes to melt like a kilogram of water from ice to water. And so with the SWE reconstruction, what we're going to do is we're going to do that. For each time step, we take how much energy went into the snowpack, and then knowing how much water we could have melted with that amount, we just keep adding it up backwards in time. So in order to do that, as Carl mentioned in his lecture, is we have to know when there's snow on the ground. So we have to find out the date at which the snow disappeared, and then we can run this backwards to the date of maximum snow. And so when we look right here, we can see we run this cell block. It's going to plot our SWE. So this is the SWE from our snow pillow that shows us basically what we're going to compare our reconstruction result to. So this blue line is an independent measurement of how much snow is at the site. And then these two red X's are the dates we're going to run reconstruction from. So we're going to start the reconstruction at this later X, which this is the date the snow disappeared. So this is where reconstruction starts. And we're going to reconstruct back to peak SWE, which is this date right here. And so with reconstruction, what we're going to do is we're going to use the energy balance components to try and estimate what this blue line is right here. And then we're going to compare with reconstruction how well we did compared to the actual measurement, independent measurement of SWE from the snow pellet. So let's see, this is basically then the reconstruction, and we're using this melt factor here. And this melt factor, which is basically how many millimeters of snow we can melt per watt of energy per meter squared. This is exactly the same as the equation we did at the very beginning of the lab in our first initial part up here, where we calculated the melt factor based on the density of water and how much energy it takes to turn snow into liquid water. So this is our reconstruction right here. Basically, we have our melt period. So from the maximum SWE date to the last SWE date, I've just put in a constant. This is from the top of the lab, how much energy it takes to melt the snow, how many millimeters of water we get out for each watt of energy. And then we basically calculate from our energy to melt, we multiply that by the melt factor. We make sure we're doing all the same calculations in the same units of measure. That's what this divide by 10 is, because some of our stuff was in millimeters and some was in centimeters. And so we get the melt per hour, which is how much energy we had available to melt, and then how much snow we can melt with that amount of energy. And then we can also calculate the total SWE, which is just the cumulative amount of melt over the whole period. So if I run that, first we can plot this melt per hour. So this is what we get from reconstruction. So for each time step, for each day, we get how many millimeters of snow we turned into liquid water based on the energy available to melt. And so here we can see each of these little parts of the graph is a different day. So remember, generally at night, the net flux goes below 0 and we're not melting. And so we have about the same amount of melt each day, but it gradually increases as later in the year, there's more energy available each day to melt the snow. And so this is our estimate each day of basically how much water melted out of the snowpack. We can then take all those and add them all together and cumulatively sum them. And if we plot that, we get our SWE reconstruction. And so we have now the total millimeters of water we have estimated in our snowpack based on the energy balance at that point. Going back from the date of last SWE to the date of peak SWE. And if we just plot both of them together, so this is just taking this graph up here of the daily and the total, and we plot them together, we can see that on any given day, just a very small amount of the snowpack is actually melting. But when we cumulatively sum that back up over time, we can see that each little bit of daily melt really adds up over time to a lot of snow melted over the course of the season. And this is how we do the SWE reconstruction. And to close it out, to look and just compare, let's now compare. This is our estimate based on energy balance modeling, not using any direct measure of SWE. Let's compare this graph to our separate measurement here we have of the measure of SWE from our snow pillow at the site. When we do that right here, we can see that we pretty much nail it and estimate independently with energy balance exactly how much snow is at that location from our snow pillow. So this is really the power of SWE reconstruction, where using the energy balance, we can very closely estimate how much snow is in a location. And when we compare it to a direct measure of SWE, they line up really well. And so this is an example of how we do this at one point. And in the next lab, what we're going to show you is that Carl and Ned have spent about 10 years taking what we've done in this lab, and instead of doing it at one point for 1 year, doing it for all the MODIS pixels for a whole MODIS tile over 20 years. And we can do this reconstruction for entire basins and entire watersheds, and historically recalculate how much water is in each pixel in the mountains every year, which is really cool. But for now, that's how we do it at a point scale. Before we close out for the night, I just wanted to see if anybody has any questions before we close out the lab.
There was one earlier question that I'm not sure I answered. Sorry, I'm looking back for it. It was in a direct message to me.
Oh, okay.
Arwal was asking about getting the relevant data from queues and running these queries himself. Arwal, do you want to ask us now that we have some time?
So, and I can, while we're waiting for Arwal, I can point everyone again. If we go up here in the lab, so let's go up. So, oh yeah.
Timbo, did you explain? I might have missed it. The CSV file that you created.
Yeah.
Was that just a straight download, or did you have from the queues data, or did you have to manipulate that in some way?
I cleaned it up a little bit, but it was basically a straight download. So if you, right here, there's a link to our website. It's snow.ucsb.edu. You can see on the shared screen. This is the live webcam of the site that I showed you the pictures of. And if you go to queues data, this tab right here, you go to model ready, level 2. We go here to queues 2011 to 2017. This right here is the data set. So if you download this CSV, it has all the data we use today. And if you're interested in other data, we have a whole bunch more data on our website, and you can browse around and look at all of it. And in addition, we have a bunch of our other products on here also. And some of the stuff we'll talk about in future labs. So,
Timbo, will you click on the other tab to the left?
Which one?
Oh, just the homepage one.
This one?
Yeah, so if you were to download data from the queues website and make it look the same as that CSV file, could you run this IPython notebook
Yep.
on, say, a different year of data?
Yeah, definitely. And this So this IPython notebook has data from 2013 to 2017. The reason, if you look on the Q's website at the model ready data, it goes back to 2011. We installed the Snowpellow in 2013. So the reason I just limited it to 2013 was there was no Snowpellow installed prior. So you can compare your reconstruction estimate to the Snowpellow estimate.
And in the lab, you only looked at a few days of data mainly, right?
Yeah, so in the lab, we just went through doing this on a few different dates, but all the data is in the lab. So when we go back here, and
You
we
can
look,
see, yeah. So
so
you can
here,
basically change the dates
Yeah.
in the lab to look at different years and look at the summer when there's no snow.
exactly.
Sometimes there might be some missing data when there's upgrades on the station.
And this is where you'd want to look right here where we do this water year variable. This is how I selected the 2017 water year and did the reconstruction. So you can definitely change that and reconstruct other periods of time. So when we did the actual calculations for energy to melt, so like right here, I'm looking at 2017. If I change this to 2014, it should also run. Yeah. So we did all the hourly calculations for the entire 5-year period to do the SWE reconstruction. We just visualized for 1 year. But up to this point, yeah, it ran it for every period of time. So you can play around. Anytime you see these dates here, you can change the dates and look at different periods. So, okay, we have a really good question from Wang Chuck right now, where he says, if we don't have Snowpellow data, then is there no method to validate the model? Or is there any other alternative to validate the model apart from Snowpellow data? So that's a really good question. And a lot of the work that we've done over the last 5 years is validating this reconstruction method a lot of different ways. So to validate it, you basically need a measurement of snow water equivalent. And there's a few different ways to do that. The Snowpellow is one way. You can go out and dig a hole in the snow. That's another way to do it and measure the density of the snow. And then the main method that we've used that we might touch on a little bit in the future lecture is something called the Airborne Snow Observatory, which is an airplane with a LiDAR that is able to estimate SWE spatially at really high resolution. And we've basically validated our reconstruction approach in many different locations at many different times of years, enough to the point where we're very confident that we have validated it enough to the point where we are confident that it works in situations that Carl mentioned, where there's a really, really clear melt season with not a lot of snowfall during the melt season, and a lot of clear sky days where you have views of the snowpack.
So I would say that at a point, this isn't actually it's not really a model, it's physics. So you're using physics to estimate energy that melts snow. The modeling part comes in when you start to extend this to the basin scale. So if you have perfect energy balance estimates from a station and you don't have a snow pit, you're using physics to calculate how much snow water equivalent was there, and you'll get the right answer. Yeah, so part of the challenge is, are our satellite estimates of snow covered area correct? And are our satellite estimates of snow albedo correct? And that's where things, get a little bit more complicated in terms of uncertainty. So, but at a point, this works perfectly. And to extend the validation part, if you wanted to do this sort of energy balance at a point in your backyard, you could, after the snow all builds up, you could dig a snow pit, and you could dig snow pits through the melt season, and you would find that it matches. And I also showed the Mount Rose sampler or the Federal sampler, which you can use to get SWE. So that's another way to do that. But there was another question from Amrit about SWE. So SWE is a depth, and you have to multiply it, by an area to get the volume of snow in a basin. I'm not sure what you meant when you said we're expressing millimeters per centimeter.
So I think what that was, I did a conversion in so there was some data that was stored in centimeters, and there was some data stored in millimeters. And so I did a conversion to display everything in millimeters. So when we talk about snow water equivalent, we generally refer to it in millimeters of water. And then we generally refer to snow depth in meters. But you could, convert between the two. So, and because of the density of the snow, usually the snow depth is a lot bigger than the snow water and the actual amount of water if you melted it out and measured how deep it was. So, well, I know we're already a little bit over time right now, but I'm happy to stick around for another minute or two to answer any more questions. But I understand if anybody has other commitments they need to get off to, I know you might have a busy day ahead of you. Feel free to leave the meeting at this point, and thank you so much for joining us. And what we'll do next Monday morning, we'll be looking at these SWE reconstructions from MODIS data that Carl and Ned have spent a lot of time working on, where we take what we did today at the point scale and we look at it across whole basins and see how we can use reconstructions and snow-covered area to give us really good understandings of what's going on in the mountains around us. At that point too, I'm going to try and set aside a little bit of extra time to go over some of that ERA 5 SWE stuff that we had in the first lab. We weren't quite able to put a lot of time on. So thank you, everyone. And yeah, Carl and I will stick around for a few more minutes in case there's any lingering questions. And then at that point, I don't know if Rajesh wants to step in and say anything right now, or if we just want to close it out.
Yes, thank you. Thank you very much, Timbo and Carl, for excellent hands-on exercise and also responding all the questions very actively. It's really, really appreciated. Thank you so much.
You're welcome.
Okay, well, I'm gonna close it out here then, and we recorded it, so I'll be sending this recording to Rajesh also once it's downloaded, and then I think they'll be posting it on YouTube so you guys can access this in the future. And feel free to use these labs also. The labs will be live. They're not going to be taken down, so you can go back and use this code and this data whenever you want to go over this material. So thank you so much, everyone, and we look forward to seeing you next Monday morning.
Thanks so much. Thanks so much, Timbo and Carl. Great lecture. Looking forward to next Monday.
Yeah, thanks for hosting us, Tim. All right, see you, everyone.
Thank you. See you. Bye-bye.
Bye.